But let's continue. So Planck, he realized that energy was quantized, and what could he do with this knowledge? Well, it wasn't him, but it was someone else who could do something with this knowledge. So I'd like to introduce the man who is known for general relativity, a man who is known for special relativity, a man who is known for the EPR paradox, a man who is known for E equals mc squared. I think, hopefully, should be able to guess who it is by now. This is, a small list of all his achievements, and it is, of course, Albert Einstein. And the reason I'm mentioning Albert Einstein is because he took Planck's idea that energy was quantized, and he observed something that was really interesting, and he called it the photoelectric effect. And it is this, basically. So what's happening is that you have some sort of light that is incident on a metal surface. So you have light that's shining onto a metal surface. And what Einstein noticed is that because the light was shining on the metal surface, electrons were getting scattered out of the material. They were literally getting forced out of the material. And Einstein said, well, how is that possible? I would never expect this. This is a bit weird that we're sort of shining light and we're forcing electrons to come out. And what he understood was that, Planck told us before, light has an energy, and this energy is proportional to its frequency. This was the equation just before that Planck had discovered that, if light is a higher frequency, it has a higher energy. So, for example, if you have blue light, that has a higher energy than red light, and that's because blue light has a higher frequency. And what Einstein realized is that at a certain threshold, at a certain frequency, the electrons would scatter from the material. Not before, only at a certain frequency. And more importantly as well, Einstein realized that it didn't really matter what he did about the brightness of the light. So for example, there might be a metal. Let's say we have a red light torch, and we shine this red light torch at a particular metal. Now, it doesn't matter if you use one torch or you collect every single red light torch in the entire world, no electrons in this particular metal will ever come off it. Doesn't matter if you collect every torch in the entire world. As soon as you find one tiny torch, make it an iPhone torch even, that does blue light, suddenly electrons come scattering off. That's the whole point. It's to do with the frequency of the light. It's not to do with the brightness of the light. And then another physicist came in to talk about things even further, and his name was Niels Bohr. And he started to understand that, well, I think there's some quantized nature in atoms. And so he basically looked at this strip that I'm showing you right here, where you can see there's purple light, there's blue light, there's cyan light, and there's also red light. And what he'd done is he'd shone all the frequencies that he could come up with of visible light at a hydrogen atom, but these were the only frequencies of light which the atom would emit in return. The hydrogen atom. These are the only frequencies of light that the hydrogen atom can emit. None other. And that was a bit of a puzzle, because why was it? And this was in 1913. Why was it that gases of atoms only gave off light at certain frequencies? Surely it should be reflecting all the colours of the rainbow. No, it would only reflect and give back light of certain frequencies. And Niels Bohr took a look at this phenomena and claimed that the whole thing was immediately clear to him, which I always sort of internally laugh at when I read it, because it's very rare in physics that something is immediately clear to you. So it is amazing that was the case for him. And this was his answer. So this could be thought of as the planetary answer, Bohr's planetary answer. He basically said, okay, well, let's think about a nucleus, and let's also think about our solar system in a way. And let's say, okay, well, let's have the electrons orbit the nucleus as if the electrons were the Earth and Saturn and Venus and the planets. And let's have the nucleus be in the middle as if it were the sun. But let's say now that you can only have certain orbits, discrete orbits, quantized orbits. You can only have certain types of orbits which have a distance from the nucleus. He would call these the levels, the electron levels, and you could only have a certain distance from the sun. And so because we had quantized electron levels, this would mean that you could only have certain types of light being emitted. The theory behind it was, okay, well, if I shine, say, red light into the atom, and it so happens that the energy difference between the, let's say, the second orbit and the third orbit happens to be the exact energy based on the frequency of red light, then the electron will go up, and it will go up to the third orbit. It will absorb it all, get all energetic, and move up to the third orbit. And then it will release it again, because naturally things don't like to remain energetic in nature. So then it will release this red light exactly back out again. And so therefore I, as a human, will observe the red light. So he's basically saying that the light tells you the energy levels of an atom. And so, yeah, I basically summarized it without even having to say anything. But that's the whole point. So the electrons will orbit. They exist in only certain orbits. They can absorb light and emit only certain frequencies of light. They absorb only certain frequencies of light, and they emit certain frequencies of light. But Bohr's model wasn't perfect. It was a good stab for sure, and parts of it remain correct, but it doesn't explain why the orbits were fixed, why they were quantized. It didn't apply for atoms with more than one electron. So for example, if you have any atom that has 4 electrons, how would they orbit? Would they be on the same tracks? Could they even be on the same tracks? And it couldn't also explain why some of the spectral lines, so why, for example, some of the colours in hydrogen were brighter than others. Why was that the case? Why were they brighter? Should brightness have anything to do with it? Yet that was what we observed. So there were still a lot of mysteries. And to understand the true nature of what atoms are, what electrons are, we needed a lot more developments to be made. So let's start to touch on some of these developments that will truly help us understand what an atom is. So how should we think about them? That is the question that remains. And for this, we need to discover some more quantum mechanics. So let's talk about angular momentum. Stay with me. This is the reason we should talk about it. So angular momentum is where it is the property of physical rotation. So it's how much rotational motion an object has. So for example, in this diagram here, we can see 2 balls, let's call them planets, and they are orbiting around each other, and the angular momentum is how much rotational motion do they have in their orbit. And the quantum equivalent of that, so when quantum mechanics was starting to be formalized properly, we said, okay, well, we need to have a quantum equivalent thing to everything that we've discovered classically. So the quantum equivalent thing is called orbital angular momentum, and we denote this by capital L. And I don't really know why, but we just do call it capital L. And so that was one form of angular momentum in quantum mechanics, but there's another one, and that is known as spin. And I think you hear this word being thrown out a lot in the kind of popular science articles or in quantum computing articles, but it is hard to actually say what spin is. It is a difficult thing to describe what spin actually is. The best way to describe it is an intrinsic, so by definition of intrinsic, this means that it just does have another form of quantum angular momentum. It just does have another form intrinsically. We observe that it does have this, and we call it spin with a capital S. And so it doesn't actually mean that they're spinning, contrary to the diagram, which kind of has this arrow that makes it look like it's spinning. This is the really sort of trippy idea. It's not literally spinning on the spot, but it has the properties as though classically it were. So if we think about a charged particle like an electron, so this denotes an electron here. If we think about an electron, it is negatively charged, and if it were to be literally spinning, then this would cause it to have a magnetic field. And so what we're saying is that the electrons aren't actually spinning, but they do have a magnetic field. And so this must be another property, and so we decided to call it spin. And so the question is, well, how would we test to see that spin was real? How would we set up an experiment for that? And the idea is that electron spin, so, it's not just electrons that have spin, but let's take electrons as an example. Electron spin induces a magnetic field. And a magnetic field is something that we know how to measure. So I'd like to show you this video. And basically we have two magnets, a north and a south. And we are assuming that one magnet's slightly stronger than the other. And so if we put a normal magnet north facing, it gets attracted to the south pole. If we put it in the middle, it just goes in the middle. And if we do the other way, it goes down. Okay? And so depending on the angle of rotation of the magnet, this will change exactly how much it deviates from its central path. Okay? But let's try this now with quantum things like an electron. Well, look what's happening. We're sending this quantum particle, electron, through this magnet, and what's happening? They're lining up. There's only two different places they can line up. No matter how many times you do it, they will only ever form two values, right? They will only ever be found on two positions on this board. And so what this means is that each electron is kind of behaving as though it were a magnet, but with only two values. And so we can say, therefore, that this spin of the electron is quantized. It's quantized because it only appears in two different exact values. So what this was saying is that, well, the electrons, they don't have any orbital angular momentum, which we've denoted by capital L. And we know this to be the case because, they weren't rotating, they weren't orbiting anything. But yet the electrons, they only scattered in two directions in the magnetic field, and they only lined up at two distinct points on the board. So what does this mean? Well, it means that, they must only have two distinct magnetic moments. They must only be able to act like a magnet in two different ways. And so what we can say, therefore, is that the electrons have two quantized spin values. The spin, the property that causes them to deviate in the magnetic field, a measurable property of the electrons, is quantized, only has two values. And so therefore we say that the spin of an electron, and the spin of a lot of things, but the spin can be quantized. Now we have something that is even more interesting, and that is the fact that everything is a wave. Even you. So I want you to imagine that you're walking, sort of like this simulation here, this GIF. Imagine you're walking just down the road, and the idea behind this was sort of discovered by Louis de Broglie. And what he said was that, so everything has a wavelength. So I want you to first take a look at this equation up here. Don't worry about so much what it means, but the important part is to say is that anything with a momentum p has a corresponding wavelength. Okay? Everything with a momentum has a wavelength. Doesn't matter how big, doesn't matter how small. When you're moving down the street, you have a wavelength because you are mass in motion. And this was a helpful concept. It would validate Bohr's previous model by showing that the electrons that orbit the nucleus, well, they have a mass and they're moving, so they must also be a wave in a sense, and that is a very important theory. It's very important to think of particles not just as particles but as waves. And for this he received a Nobel Prize in 1929, so it was a huge achievement. And now we're just on the cusp of understanding. By bringing all of these concepts that we've just talked about together, we're just on the cusp of being able to approach what electrons are, what atoms are. They're complex things, but we're just entering modern quantum theory, just after 1924. And so we have to introduce Werner Heisenberg and his uncertainty principle. So this is Werner Heisenberg, German physicist, and he derived this incredible equation. And so I don't want you to worry so much about what's happening on the right side. Just think of this as a number. But what's happening on the left side is very important. This symbol here with X basically means the uncertainty in the position of something. So let's say an electron or an atom or something. This would be the uncertainty in the electron's position, and this would be the uncertainty in the electron's momentum. And so what he's saying is that this will always be greater than or equal to this number. It can never be zero. So that both the uncertainty of the electron's location and the uncertainty of how far it's moving, in what direction, with what speed, can never be zero. You can never simultaneously know both properties at the same time. It is not possible with 100% accuracy. It's not an experimental limit. It is a fundamental universe limit. And that is very weird. It is almost as if the universe is trying to hide something fundamental from us. It is as if to say, it doesn't matter how good your experimental apparatus, doesn't matter how amazing you become at building this experiment, or how good you'll become as a physicist, you will never truly know both where an electron or anything quantum is and its momentum at the same time. You can't know that. And I realize this should be a P. And so there's a limit to how much we can simultaneously know about certain pairs of properties. So the more we know about an object's position, the less we can be certain about its momentum. And although this rule is this universe rule is very dominant on the quantum scale, on the very tiny scale, such as with electrons, there is technically no size limit to where this rule doesn't apply. So it could apply with someone as big as a human, but the thing is, it's such a tiny effect that it doesn't really change anything, and we have so many particles that you can think of it as being completely negligible. But with something like an electron, it's very, very dominant. We literally cannot measure where an electron is and what momentum it has at the same time. It's literally not possible. So now we have to talk about the sort of self-proclaimed GOAT, if you will, or when I say self-proclaimed, I mean I'm proclaiming him as the GOAT of quantum mechanics, Erwin Schrödinger. And he is an Austrian-Irish, I believe, physicist, born 1887 to 1961, and he came up with arguably the most famous equation and definitely the sort of foundational building block to modern quantum theory, and that is the Schrödinger equation. And this equation is very interesting because it has this symbol here, which is the Greek symbol known as psi. And what this equation basically describes is the evolution of any quantum state. So the psi is surrounded by this interesting sort of mathematical structure here, which we don't need to go into the detail, but what we should understand is that what this symbol is describing is the wave function of a system. So let's say we have a quantum system. You've got it in you've got a quantum system in a bowl. Well, let's say, and Schrödinger is saying this, let's say we're going to call this quantum system, we're going to describe it by something known as a wave function. It's a mathematical thing, and it will describe the entire quantum system. And he's saying that, well, it's going to change in time, it's going to evolve, and we can work out with this equation how it will change in time, and it will be related to the energy levels, the quantized energy levels of this system. That is what he's saying with the Schrödinger equation. It is a very, very versatile, very, very useful equation. But I suppose, in a sense, he's even more famous for Schrödinger's cat. And this is a very, very famous thought experiment that helps to explain a quantum phenomena known as superposition, but actually it also helps to explain one of the main challenges in quantum mechanics. So let's imagine that we have a cat in a box, and the sort of answer to this thought experiment is that the cat is both dead and alive at the same time. And you might say, well, how's that possible? It can't be dead and alive at the same time. But it kind of can. So here's how you set up the thought experiment. You find a cat, and you place the cat inside the box with a vial of poisonous gas attached. Okay, so you can see the green bottle there. That's poisonous. It will die if it inhales these fumes. And then you set up some sort of random event that can smash the vial. So it's random. You don't know when it's going to happen. Let's say it rolls a dice every 3 seconds. And if it's a 6, it will do it, right? You don't know when it will do it, but it will happen at some point. And now, assuming you're outside of the box, there's no noise can escape from the inside, you can't see inside, how do you know whether the cat is dead or alive without checking? How can you know? And the answer is, well, and as Schrödinger says, you can't. You can't really know at all. And so therefore, let's say, that this is the phenomena that I'm trying to describe. This is what is actually happening at the quantum scale. It's superposition. The cat isn't alive. It isn't dead. Before you check, the cat is actually in a state of being both dead and alive. Once you check, you can verify whether it is actually dead or alive. Once you open the lid to the box, you'll know whether it's dead or alive, of course. But during that time where it remains unobserved, it is in a state of being both dead and alive.